Hi, welcome to my science tutorial. In today's video, we're talking about rate equations and we'll also look at the calculations involved, how to go about them. Now, before we proceed, we have a video on the rate law equation. If you haven't seen that, then you can check it out in our playlist. In our previous video, we did mention that the rate law equation is derived from what we call the rate determining step. Rate determining step, in short RDS. Okay, so we know that this RDS, or rate determining step, is the slowest among series of reactions that take place to complete a main reaction. So it's the slowest. And then we look at a general equation such as this: A plus B, and then our A has X and the B has Y, giving us a product. And we say that if we have something like this and we want to write the rate equation, then the rate equation is going to be given by R is equal to K, and then we have the concentration of A raised to the power X and the concentration of B raised to the power Y. Alright, so we look at that and we said the R here is our rate, the K is a specific constant rate, that's the constant, and then A and B are the reactants, and then we have the X and the Y being their mole. Alright, so X is the order of reaction with respect to reactant A, and Y is the order of reaction with respect to reactant B. And then when we add the two, X plus Y, we have what we call overall order of reaction. Overall order of the reaction. Alright, so there are some few things we have to take note of before we proceed. And the first thing is that if let's say if a particular reaction is not said to be the rate determining step, then their respective moles, in this case X and Y, cannot be given as the order of the reaction. It means the order of the reactants over there has to be determined experimentally. So when we have an equation such as A plus 2B given as a product D, and if they said this reaction is not an RDS, then we can't write the rate equation to be R being equal to K, and then we have our reactant A, and then we have B raised to the power 2. No, this can be our rate equation. Alright, how then do we write it? You write it with a general formula, which is R given as K to the X, B to the Y. So X and Y will be determined experimentally. Another thing we have to take note of is what we call the molecularity. This is talking about the number of reactant species. What is reactant species? Like atoms, molecules, and or ions. That actually are found in the rate determining step. Okay, so we can just put it this way and say that it is the number of reactant species that take part in the RDS of a given reaction, in the rate determining step of a given reaction. So if we have the reaction B plus A2 to give us BA2, and then if the rate determining step of this reaction is if RDS is BA plus A2, giving us our BA2 plus A, then in this case we will say that the molecularity is 2. Molecularity is equal to 2, because talking about the reactant species, we have the atom B, and we also have the molecule A2, so that means our molecularity is 2. Now another thing we have to take note of is that anytime we have a rate equation and there is and one of the species does not appear in it, I'm talking about the reactant species, if it doesn't appear in the equation, then that means that that particular reactant, or we can say the order of reaction with respect to that particular reactant is 0, and so we will not see that in the rate equation, and that simply means that the reaction rate does not depend on that particular reactant. Now if this reaction A plus 2B given us D, if this reaction is a rate determining step and you write the rate equation, R giving us K, concentration of A, and that of B to the power 2, then we know that the mole of A is to the power 1, so we won't write that one there. And if B is 2, if the mole of B is 2, we write the order to be 2. So the order of the reactant A is 1, and so we'll call it first order reactant. And if we talk about B being raised to the order 2, then we'll say that B is a second order reactant. What if it is to the power 3? They will call it third order reactant. Now there are some important things we have to note for a first order reaction. We're talking about things like having a rate like R equals K, the concentration of A to the power 1. Then when we increase the concentration of A by n times, then definitely we're going to have the rates of the reaction also increase by n times. So our rate here is going to be n Okay, so if our initial rate is R, then let's call our final rate after increasing the concentration R1. So in this case, when you observe, we can then say that our R1 is equal to NR. That is N times the initial rate of the reaction. Now, what about a second order reactant? If we have our rate being equal to K, and then we have the square bracket of A to the power 2. What if the concentration of A is increased by n times? If R is this, and then it is increased by n times, then what is going to be our R2? Our R2 is going to be n to the power square. So when we have r2 to be equal to n squared k square bracket a to the power 2, then we can see that our r2 is equal to n squared r, because we know that our r is equal to k square bracket n a to the power square. So this simply means that our r2 is equal to n squared r. This is a question on rate. There's a question on rate, and it said in a certain reaction, the rate determining reaction is A plus 2B given as C plus D. And now it says A, write an expression for the rate equation. B, deduce what will be the effect on the reaction rate by I doubling the concentration of A, and II doubling the concentration of B. And then C said, how should the concentration of B be changed in order to halve the reaction rate? And A said, write an expression for the rate equation. Now, the most important thing we have to check out is whether this reaction is a rate determining step, and that is stated in the question that the reaction given us is the rate determining step. So that is simple. We'll go ahead and write our rate equation. That will be, let's say A. So A, our R is going to give us our specific constant, rate constant, and then we have reactant A, then we have reactant B raised to the power 2. Now this is the order of reaction with respect to B, and the order of reaction with respect to A is 1, so you don't have anything at the top there, which means the moles of these reactants we know are equal to the order of their reactions, because it is the rate determining step. Now let's look at B. Now I says that we double the concentration of A. We double the concentration of A, but let's remember that when we double the concentration of a first order reactant, that is when we have a rate such as this, and then we increase the concentration of A by n. We increase the concentration of A by n such that we have our new rate, which is R1 to be equal to K into brackets NA to the other one. Then we can say that R1 is equal to NR. R1 is equal to NR. Okay. In this case, our N is equal to 2 because we are doubling the concentration of A. So when you write our rate equation this way, we have a constant, and then we have 2A, then we can write our new rate, which is R1 again, to be equal to a constant, and then we have, okay, let's bring the 2 out, so we have A to the power 2. So how do we know that the rate will double? Let's divide this R1 by the initial rate over here, by this initial rate which we have written as A. So we will now have our R1 divided by R. This will be equal to 2Ka bracket B square, all divided by our K, and then we have our A in bracket, and B square. So what is going to happen? We're going to have this cancel out this, as well as this cancel out this, and a K also cancelling out. So what is going to be left is R1 over R being equal to 2. Now we are looking for R1, so this means that our R, this implies that our R1 is equal to 2 times R. So how do we conclude this? We can now say that when we double the concentration of A, we'll have our rate of reaction to be double. That is going to be 2 times R, 2 times the initial rate of the reaction. Okay, now let's look at the II. This time we are doubling the concentration of B, but remember that B is a second order reactant, so let's see if we have R to be equal to K into bracket B square, and now we are doubling it to give us R1, and then we have K into bracket N B. We are increase the concentration by N to the power square. Now remember that the effect is going to be that we'll now have our R1 to become N square. That is the rule for a second order reactant. So we'll have N square, and then we have a constant, and then we have in our bracket B square. So this simply means that for a second order reactant, our new rate of reaction is going to be at N square the initial rate, N square or the initial rate. So let's look at what happened. Okay, so let's call it R2. Let's call it R2 when B is double. So when we take R2, have our K, our A, then we have 2B square. So this is simplified as 2K. We have the square bracket of A and B square. So how do we do then? Let's divide R2 by our initial rate, which is R. So this is going to be 2K, and then we have our A B square, which is going to be divided by, okay, I just noticed something is wrong. So per this rule, if we have 2b to the power 2, per this rule, it means that we should have 4 times the rate over here. So let's see, this is going to be 4, which means this also is going to be 4. So let's divide by the rate, which is our K A B to the power 2. So again we have this cancelling out, this cancel out, and this cancel out, which means our R2 divided by R is going to be equal to 4. So when we make R2 the subject, remember that's what we are finding, it's going to give us 4 times R. So when we double the concentration of B, which is a second order reactant, we are definitely going to multiply the rate of the reaction by 4. So to do that simply, you can just come here, we can come here straight and write our R2, and then in place of N we'll bring our 2, that is, we are doubling the second order reactant, so 2 to the power 2 times R. So we find out that our R2 is going to be equal to 4R. So that is it for the B. Now the C said, how should the concentration of B be changed in order to have the reaction rate? Okay, so let the concentration of B become asterisk when it is double, b asterisk when it is double. So for the half rate, it is going to be 1 over 2 r, giving us KAB asterisk square. So because we are halving it, that means we are dividing the rate by 2. So this is what it will look like. It will look like when we divide it by 2. So what do we do? Let's divide this by our initial rate. So let's say 1 out of 2 r divided by our initial rate, and it is going to be our half rate divided by the initial rate. So let's see what can cancel out. We can cancel the constant. Our a is also going to cancel out, as well as the r. So this is going to give us 1 out of 2, which is going to be equal to our b asterisk b asterisk square divided by b square. So what if we multiply through by b square? It means we are going to have okay, let's bring it to the top here. So we're going to have 1 out of 2, and then we have b square, which is going to be equal to b asterisk square. Okay, so remember we are looking for b asterisk square, which is the concentration of B needed in order to halve the rate of the reaction. So because this is square root, let's take square root of both sides. So square root of half b square, which is going to give us the square root of b asterisk to the power 2. Now this is going to cancel out, so we now have b asterisk to be equal to the square root of 1 out of 2 b squared. So simply we'll say that our concentration, which is b asterisk, that is root of 1 out of 2 that's the root of b square, and remember this will cancel out, so we're gonna have b asterisk giving us b, concentration of b, times the root of 1 out of 2. So this is the end of the video, and then we found out that to be able to halve the rate of the reaction, then we need to multiply the concentration of B times the root of half. If you like this video, don't forget to subscribe and hit the like button so that you get notified for our new tutorials. Thank you.